So hopefully you have a general understanding of Redshift clusters. This is an area where we went a little deeper in that first course, so we're just going to jump right in here. In 3 sentences, a Redshift cluster is made up of a single leader node and then one or more additional nodes. Your queries, applications, connections, really anything only ever interacts with that leader node. To them, it is the database. The leader node then compiles any query given into individual instructions that it divvies out to each node across the cluster in the form of machine language. Now, in a later module, we'll dig deeper into the whole query optimization process, and also how to investigate your query plans for further performance tuning. For our purposes right now, it's just important that you understand that the leader node does the work of compiling and distributing instructions out to the other nodes. The nodes where the magic happens. Also important is knowing that each node is further divided into node slices, roughly 1 slice per CPU core, ensuring dedicated storage, memory, and CPU all have the potential to be fully involved in queries in parallel fashion. This is what is meant by the term massively parallel. As data sizes and query complexity grows, Redshift can scale out to more and more nodes and node slices, and it scales in a nearly linear manner. When done right, a query of terabytes can be just as fast as one of megabytes or gigabytes, and how Amazon can tout Redshift as a petabyte-scale data warehouse solution. But let's back up for a second. I just said the operative phrase, when it's done right. So what do you need to know to do it right? Critical to taking advantage of the massively parallel potential of Redshift is setting up your nodes, node slices, and distribution of data in a way that allows the leader node to take true advantage of all that potential. When first setting up your cluster, you select the node type, your options being either dense compute or dense storage. My best advice here is keep in mind that while the number of CPUs on, say, a dense compute large or an 8x dense compute large versus a dense storage large or a 8x large are nearly identical. The ratio of CPU to terabyte, however, is where the major difference is. Now, these stats change from time to time, but the message is clear. Dense compute means a whole lot more CPU per terabyte of storage, and it's on SSDs, meaning that the storage you do have can feed all those CPUs at a much faster rate. With that in mind, when would you ever choose dense storage? Well, the benefit of dense storage is a much reduced cost per terabyte. And not all data warehouses require all that query overhead. When your schema and data distribution styles are in line with the type of node that you've selected, the performance is still quite high. Now, only you can make the choice of node here. After all, it's your wallet. After this choice is made, however, it is critical that you structure data distribution to correctly match the profile of data being stored. Matching slices, CPUs, and data distribution style is the critical skill when architecting your solution. That's what I meant by doing it right. So starting at the top, when it comes to data distribution, you have 3 choices: even distribution, key distribution, and all distribution. I hope that that's not news to you. If you need a refresher, we covered these briefly in the companion course. Here, let's go deeper. Let's find out what that actually means, use some demos to drive it home, and really help you get a true understanding of the decision that you have before you.